let's remind ourselves where we've been. In section 4.1, we introduced this idea of a vector space and then the idea of a subspace. And those are kind of abstract ideas. And then in section 4.2, we focused in on two specific subspaces that we could learn a little bit more about. And those specific subspaces were the null space and the column space. And as part of that, we found ourselves creating these things called spanning sets. So we had this idea of a spanning set. And so we talked about how the spanning set was not unique and that you could actually just add extra things to a spanning set and you wouldn't change the size of the space, because you could be adding zeros or be adding linear combinations of things. And so now we're going to focus in on this idea of a spanning set plus the idea of linear independence. And that's going to combine to give us this new concept of a basis. Okay. And a basis is it's not hard, but it's a big deal. It's something that's going to stick with us for the rest of the course. Okay. So we're basically focusing in on this idea of a basis. All right, so section 4.3, not on page 1. Section 4.3 on linearly independent sets and bases. So let's start with some reminders. So recall the previous definitions of linearly independent and linearly dependent. So we're now going to think in terms of a vector space V rather than just being in our old Rn. So let's look at a definition. So we said an indexed set of vectors V1 to Vp in Rn is said to be linearly independent if the vector equation x1 V1 plus plus xp Vp equals 0 has only the trivial solution. What do we call this equation right here? What's the name of this equation? Yeah, thank you, Evan. The homogeneous equation. And it's the homogeneous equation because you have that equals 0 on the end. So if the homogeneous equation has only the trivial solutions, it's linearly independent. It's linearly dependent if there are non-trivial solutions. Okay. And so what I want to point out here is that the only thing we're going to change from this old definition to the new definition is now, instead of having Rn, we're going to say V, because it's just some arbitrary vector space. Okay. So same definition, it's just we replace Rn with V. Okay. Also recall that an index set V1 to Vp of 2 or more vectors with V1 not equal to 0 is linearly dependent if and only if some Vj is a linear combination of the preceding vectors. I feel like this is one of the ones that you guys proved on an assessment, as I recall. So if a vector space is not Rn, described with the easily solved matrix equation Ax equals 0, then we're going to need theorem 4 to show a linear dependence relation to prove linear dependence. Let me see if I can phrase this statement differently. Okay, so if you want to show linear dependence, then you might say to yourself, oh, I know what to do. I'll just use matrices. And you'll solve AX equals 0, right? But the catch is that this only works when your vector space is Rn. And so if it's not Rn, if you want to show linear dependence and it's not Rn, then you're going to have to use the equation above, the theorem 4. Show theorem 4 holds. That is, you got to find the non-trivial solution. Okay. All right, so let's look at example 1. So I want to discuss the linear dependence or independence of the following set of continuous, this is the continuous set of continuous functions on 0, 1. Let's make sure you're tracking. Let's look at sine t, cosine t. So if I want to show whether these are linearly dependent or linearly independent, I could first of all say sine t, cosine t, this is not in the world of matrices. So here I could try to solve, like, maybe I'll use A's and B's instead of C1, C2, C3, something like that. So I have A sine t plus B cosine t equal to 0. So are there any A's and B's that will make sine and cosine exactly cancel out? So if I choose 0, then it would work. But there are no non-trivial solutions, right? And just to be clear, I'm not saying that they would never equal 0, but I'm saying that if you graphed the left side of the function, suppose you chose 2 and 3. I'm saying if you graphed something like 2 sine t plus 3 cosine t, would you get a graph that was the horizontal line y equals 0? And no, you wouldn't. So here you have only the trivial solution. So therefore, you would say that sine t, cosine t are linearly independent. Folks okay on the purple there? Yeah. And that wasn't a proof. That was just kind of using what you know of trig. All right, how about the next set? So if we looked at this and we wanted to solve A times sine t cosine t plus B times sine 2t equal to 0. Can you think of some A's and B's that would make this, some interesting A's and B's that would make this true? So if we let from hui, yeah, interesting, so not equal to 0, that's correct, Ben. So if we let A equal 2 and we let B equal -1, this works because 2 sine t cosine t is the same thing as sine 2t using the double angle. So that's telling us that there are non-trivial solutions. And since there's non-trivial solutions, we can conclude that the set is linearly dependent. not only this, we could use this second black example here to show what was going on in theorem 4. So if you compare this one here with what's going on in theorem 4, we would be saying an index set of, in this case, v1 and v2, two or more vectors, we're good. v1 not equal 0, good, is linearly dependent if and only if one of the vectors is a linear combination of the preceding vectors. So in this particular case, notice what we're saying is that sine 2t is a linear combination of the preceding vectors. It's 1/2 of sine, well, it's, sorry, 2. I got that backwards. It's 2 of sine t cosine t. So see if we can get the, here we're showing what's going on in theorem 4. Let's see if we can get our colors in here. If some vj, the vj would be this one. Notice it's the second one on the list, okay, is a linear combination of the preceding vectors. Here's the preceding vectors on the list. In this case, there was only one preceding vector. What is the, I got a question of what does the green highlight represent? So what I'm trying to say is that the second vector is equal to a linear combination of the first vector, of the previous vectors. All right, so we've talked about linear independence and linear dependence now in the context of a linear transformation, which is a slightly broader concept than the world of matrices. They're similar, they're related. You'll see how related as we proceed, but we've talked about them in this new context. And now we're going to introduce our main new concept, which is this idea of a basis. So let H be a subspace of a vector space V. An indexed set of vectors B equal to B1 to BP in V is a basis for H if it has two conditions. Condition 1, the vectors are linearly independent. And condition 2, the space is spanned by the vectors. So 2 conditions: 1, linear independence; 2, span. So let's look at an example here. What can we say about an invertible matrix A that's n by n? So we can say that, first of all, we can say that the columns of A are linearly independent because you have a pivot in every column, right? And then 2, we can say that the columns of A span Rn because you have a pivot in every row, okay? And so if you have that the columns are linearly independent and the columns span, what can you conclude? From Kevin, from Ben, from Gerald, it's a basis. So we can conclude that the it in this case isn't the matrix, it's the columns. So we can conclude that the columns of A form a basis for Rn. Thanks also Megumi and Gerling. So the columns of the identity matrix E1, E2, En is called the standard basis. For Rn. And remember that in R3, your standard basis are your old friends. So here's your E1, your E3, your E2. What else did we call E1? I think we also used to call E1 things like I, or did you guys, what did you use X hat in engineering? What other names did you use for it? Is that right? Yeah, X hat, something like that, or I hat, stuff like that. So number of different names for the same thing. So your old IJK have gotten replaced. They got new names. Now they're going to be E1, E2, E3, E4. The reason that they were using E's instead of IJK is that now we're in a world where there are more dimensions. So now we're in this world of n dimensions, and there aren't enough letters to guarantee that you could cover all n dimensions. So we just want to number them. Questions? Keep going. All right. So we want to determine whether these three vectors form a basis for R3. And so if we want to know if they form a basis, then we're looking to answer, determine if they have two qualities. What are the two qualities that they need to have? They've got to be linearly independent, and they've got to span. So any great ideas for how to determine if three vectors are linearly independent? Yeah, from Abed, we could ref it. So we can take these three vectors and we can turn them into a matrix. We're going to ref the matrix that's made up of V1, V2, and V3. And if they're linearly independent, we'll get a pivot in every column. So we ref it, and when we do it, we end up with 1, 0, half, 0, 1, 2, 0, 0, 0. So what does this result tell us? So it tells us that the three vectors are linearly dependent. So you have this free variable. Well, it's not really free variable. You've got your no pivot, right? So linearly dependent. Okay. And specifically, let's think about what this 1/2 and this 2 represent. What those are telling us is it's telling us that the third vector is equal to 1/2 of the first vector plus 2 of the second vector. Okay, let's see whether that holds up. So it's telling us, here's the 1/2, here's the 2. Let's see if this works. So 1/2 of the first vector would be 1, 2, 2 plus sorry. 1, 2, 2 plus 1 minus 2 minus 4. Let's check it out. Equals the V3. Yeah, and as Alex and Megumi said, our conclusion is, so this is not a basis. Okay. Questions so far? So you might say to yourself, it looks like this green one, V3, is linearly dependent. Let's just chuck it out. And so I'm just going to keep those first two vectors right here and just consider them. So now I've only got two vectors. So maybe since I only have two vectors, we could ask, is this going to be a basis for R2? We got two vectors, R2, so maybe that could work. What do you think? So I've got some no. I've got from Felix that it doesn't span R2, so maybe why isn't, so I agree with you that it's a no, but why not? Yeah, from Ryan, yeah, the V1 and V2, they live in R3. So since they live in R3 here and not R2, there's no way that it's going to work. And for Megumi, we also have some pivot issues. So. Questions? All right, so far we've been working in the world of vectors. Let's go back to the world of polynomials. And so I want to establish a basis for the world of polynomials. So if we let s equal to 1 comma t squared comma dot 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 comma t to the n, we can ask ourselves, is s a basis for Pn? And the answer is going to be yes. We're going to call it the standard basis for Pn. So first of all, we've got to ask ourselves, is it linearly independent? So if we want to know if it's linearly independent, we could solve for like a1 times, a naught times 1 plus a1 times t plus a2 times t squared plus an times t to the n equal to 0. And I could say if I have a n degree polynomial that's equal to 0, like, and I'm not talking about x-intercepts here or t-intercepts. What I'm talking about is a a flat line, like that it's a horizontal line. Sorry. So that's what I mean when I say equal to 0. So in order to have a polynomial always be 0, what can you tell me about all of those coefficients? Yeah. From Felix and Croy and Evan and Alex, they've got to all be 0. So what does that tell you about 1 comma t squared comma dot 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 to t to the n? What does this tell you? From Evan, this tells you that it's Li, it's linearly independent. The reason it's linearly independent is because you have only the trivial solution to the homogeneous equation, right? So this equals 0 means you have the homogeneous equation. You only have the trivial solution, so it's linearly independent. So 2, we need to look at span. Okay. So we could ask ourselves, do these vectors span Pn? And I think it should be clear. Okay. And they span it because of the way they're constructed. So therefore, we could conclude that S is a basis for Pn. All right. So a basis is an efficient spanning set. So we talked about spanning sets right at the beginning of the day. So it's an efficient spanning set. And when we say efficient, what we're trying to say is that it has no unnecessary vectors, no extra vectors. And so if you think about the example that we did earlier, where we had the V1, V2, V3, we showed that V3 was equal to, I think, a half V1 plus 2 V2, something like that. I'd like to walk through example 5. So in example 5, we have the question, let H equal the span of V1, V2, V3, as in example 3. And I want to show that the span of V1, V2, V3 is equal to the span of V1, V2. And I'd like to begin this by asking that you recall that we already showed that V3 was equal to a half V1 plus 2 V2. V3 was equal to a half V1 plus 2 V2. And this tells us that V3 is in the span of V1 and V2. Okay. Since V3 is in the span of V1 and V2, that's enough to show that the span of V1, V2, V3 is equal to the span of just V1 and V2. And again, that's because V3 was in the span. How did I know it was in the span? I knew it was in the span because of the fact that it's a linear combination of V1 and V2. So let me just hit one other thing here, or a couple other things. One is just a notational bit. Notice that in general, I'm using the braces, the curvy brackets, when I'm working with span. Over here on the right, I use normal parentheses. You have a little bit of freedom. In general, I use the braces. I forgot in this case. I think this is a place where you can use whichever one makes you feel good, because math is all about feelings. Second thing I want to point out is this use of the word span. So we're using the word span sort of in two different ways. So one way we use the word span is we're using it to say do something. Do something. And in this case, what is that something? It's have a list of all possible linear collections. So make all possible linear combinations. Okay. And so we would talk about something is in the span, or things span, or something along those lines. But the other way that we use the word span is we're using the span to describe, we're saying vectors span a space, and we say vectors span a space, we're saying that they are the things that you're going to use to make that linear combination. So the other one is we would say span. We'll say that vector span when they're like the building blocks.
It's kind of sad because you see people definitely sort of blinded by their own lights. No, unfortunately, either by money or by the sort of arrogance.
So it's almost like in the first case, we're talking about using the word span to say do something. In the second case, we're using the word span almost like it's a description. So it's kind of two different ways of using the same word. That's the end of example 5. And when we pick this up again on tomorrow, we will talk about this theorem 5, the spanning set theorem. So we're going to continue in section 4.3, talking about linearly independent sets and bases. And so we did some examples yesterday, and we're going to pick it up today with theorem 5, which is called the spanning set theorem. So the theorem reads as follows. So if we let S equal V1 to VP, and that be a set in some vector space V, and let H equal the span of those vectors. Let me make sure you're tracking what's going on. S right here, this is a finite list. And then the H, this is an infinite list, assuming that some of the vectors are non-zero. Of all linear combination. So that's what those two sets are. So then we go on, and it says that if one of the vectors if one of the vectors in S, say VK, is a linear combination of the remaining vectors in S, then the set formed from S by removing VK still spans H. And B, if H isn't equal to 0, some subset of S is a basis for H. So we got at this idea yesterday when we had the set above, and we basically said that in the set above, we could treat that V3 as being redundant, like extra information, so we could chuck that vector out. So now we're trying to prove it in a more general sense. And I'm going to erase these marks because they don't really help us. All right. So we've got a proof here, and we're going to begin our proof the same way we usually do. So here's our claim up above. And then we can say, let S, H, and V1 to VP be as given. Above. Okay. Scary looking. All right. So the first thing we're going to do is we're going to do some organization of these vectors. So we have this V1 to VP, and they're not in a very good order for us. So we're going to do some like organization. So let's reorder or re-index V1 to VP. And we want to do it so that we can accomplish two things. So that first, we want to have that we have a bad V last, so that VK is now VP, where VK was a linear combination Oh, I'm sorry. Didn't give you enough space here. You're going to need a piece of scratch paper here to work on the back of notes. This particular proof is about a page long. So if you need to take a moment out and grab a piece of scratch paper here, that'd be a good idea. Okay. And then the second thing we want to deal with in this is we want the vectors to be linearly independent until they become linearly dependent. Okay. So this is a little bit strange, and so I thought maybe I would bust out some props to try to explain what we're doing here, because it's actually really easy, but the wording makes it look kind of hard. So let's see how this works. Can I leave the notes? Okay. All right. So I went for some complicated props. You might recognize some of these guys in a moment. Okay. Where's my 7? Oh, there it is. So I'm going to bust out some Legos here. So notice that some of these Legos are like full Lego guys, aka minifigures. Okay, and other ones are just partial bodies. Okay, and okay. Where's oh, that's so weird. The angle's funny. Sorry. It's funny. The angle's funny. It doesn't let you see them all. See all the labels, right? Here's 7. Okay. So far, so good. You can't see your 1. Give me a thumbs up. Okay. So I've got 7 minifigures. I think you can see them 1, 2, 3, 4, 5, 6, 7. And they are, so this is the equivalent to my list S. Okay. So it's that original list that's given. But this is a weird order. And so imagine that you're a kid, you're playing with Legos, or you're over at a friend's house, you're playing with Legos, and you pull out these 7 minifigures. And so what you want to do is you want to reorder that list. And so what we're going to do is we're going to, actually, I'm going to swap it just for the time being. We put the girl on the end. Okay. So what I want you to notice is that in this particular order, I have a good one first, a good one last, right here. Good one last. And then I have a whole bunch of bad ones kind of in the middle. And so what I want to do is I want to guarantee that I have a bad one last. So that first bullet where I said, so VK is now VP, and that VK was linearly dependent on the others, is saying I want to guarantee that I have a bad Lego last. Okay. So now I have a bad one at the end of the list. Does that make sense? I got a bad one at the end of the list. The second bullet says, hey, notice that I have good Lego, bad, bad, good, good. I want to put all of the good ones first. And so I'm going to just move these around so that all the good ones, this one minifigure has bad legs. He's like got weak knees or something like that. He's gonna have to sit down. Sorry, guy. You're not strong enough to stand. Okay. So I have a bad Lego last, and I have all of the good Legos here at the front end. Okay. So notice that the L that's here, the L marks the end of the good Legos, and the P, can't quite see it. The P here represents the last Lego, and the way we've chosen it is going to be a bad one. Does that make sense? So that's what, when I say re-index, reorder, I'm just saying put them in an order that makes sense for us so we know what we're talking about. Yeah, VK from Andrew. VK is the bad one. Yeah, so VK was the bad one. It used to be somewhere in this world, but we've made sure it's the last one on the list. So now the bad one is the bad one is the VP. Back to the proof. Okay, so after we've done this reordering, now we have V1 to VL. Okay, and then it keeps going, and you have VL plus 1 to VP. Can you hear me?
Yeah.
Cool. All right. Okay. And this VP right here, this is the old VK that was kind of like in a weird spot. I'm looking at Ahmed, I'm looking at your question. Does that say V underscore RM? Where? L plus 1. Yeah. Thank you, Andrew. All right, so now we're going to go into our proof. So remember that part A, we went back, part A says that if one of the vectors in S, say VK is a linear combination of the remaining vectors in S, then the set formed from S by removing VK still spans H. And so that VK, this is now our VP. That is something happened weird. All right, so if we let X in H be given, so it's in our space, then what does it mean for it to be in H? It means that it's within the span of these vectors. So there exist C1 to CP such that X is equal to C1 V1 plus ... plus CP VP. We also know that VP, we also know that, is Zoom glitching for everyone or is it just me? This is a very strange day. Very weird. Okay, thank you. Okay, let's keep going and just see what happens. So remember that this VP is a linear combination of the other vectors. So we know that this first thing is true, and we also know that VP is equal to some D1 V1 plus dot 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 plus DP minus 1 VP minus 1. This is just saying that the VP is a linear combination of the other vectors. And so we have VP here, and we have VP there, and so we can substitute in. So this tells us that X is equal to C1 V1 plus all the way to CP minus 1 VP minus 1 plus CP, here's the CP, and then we're going to replace our VP with all of this garbage right here. You could combine like terms, and so this is saying you have C1 plus CP D1 V1 plus dot, 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 the last term being CP minus 1 plus CP DP minus 1 VP minus 1. Let me make sure you're seeing where those come from. So here's a, for example, here's a V1 and here's a V1. And so I could combine those together to give me this much V1. Similarly, here's some VP, here's some VP, distribute, and now we get this much VP. So what this is telling you is that we can form X from the set without VP. In other words, therefore, the set formed by removing the old VK, that bad Lego, still spans H. Which is the end of part A. There's something weird in the formatting that happened. I'm not quite sure what, but so we have. So that's part A. Let's go on to part B. Part B asked us to show that if H is not equal to 0, some subset of S is a basis for H. So we can focus in on B. So it says that by construction, the way we set it up, the reordered set vectors vectors v1 all the way to vl, okay, are linearly independent. Well, I should say VP, maybe I'll go to VP, are linearly independent until they aren't. So that tells us that thus V1 to VL are linearly independent and span H, thus they are a basis. Therefore, the set V1 to VL is a basis for H. Questions? All right, let's keep going. So let me make sure that the point of the last theorem is clear. So the point of the last theorem is that if you have a set of vectors that spans a space but isn't linearly independent, you can chuck out all the extra vectors until you get a basis. So you can get rid of the extra information. And so we're going to do that in this next example. So we already know how to find a basis for the null space of A, as we saw that the row-reduced system that describes the solutions of null A is already linearly independent. However, finding a basis for the column space that doesn't have unneeded vectors is our next step. So we want to find a basis for the column space. So here, suppose I had some matrix B, and my matrix B had 5 columns. So here's B1, B2, B3, B4, B5. And after we go through, actually, these are the 5 columns. They're already shown. So those 5 columns are already put in some order that is in reduced row echelon form, just because that was convenient to us. And so you'll notice that there are pivots in the first, second, and fourth columns. And what that tells us is it tells us that the corresponding columns, B1, B2, and B4, are going to form a basis for the column space. So it's these same vectors, the ones that correspond to the pivots. Okay. So in this particular case, notice that B was already in reduced row echelon form. Well, let me make sure it's clear why this is the case. we can exclude B3 and B5. So we exclude B3 and B5 because they're redundant, because we have that B3 would be equal to minus 3 B1 minus 4 B5. Sorry, B2, I said 5. And B5 is equal to 4B1 minus 5B2 and minus 2B4. Just so you're tracking those coefficients, these coefficients are the same as these numbers, and these coefficients are the same as those numbers. Gerald asked, do B1, B2, and B4 span? There's no pivot in every row. They don't span R4. You're right, there isn't a pivot in every row, so they don't span R4, but they do span the column space of B. So it depends on, so do they span? Yeah, what are we talking about? What's the space we're talking about? Does that make sense, Gerald? All right, so let's see if we can do something a little bit more generic. So if we want to find a basis for the column space of A, where A reduces to matrix B in the previous example. So in this case, we're saying that if we started with A, this ugly thing that's given, it's going to row reduce to the matrix above. 1, 0, -3, 0, 4, 0, 1, -4, 0, -5, 0, 0, 0, 1, -2, and zeros across. So we can row reduce it Texan style there. And at this stage, we're going to identify the pivots. And those pivots are going to tell us which columns in the original matrix are going to form a basis for the column space. Okay, so this says, this orange stuff is telling us, is use columns 1, 2, and 4 as a basis. As your basis. Or if I phrased it more cleanly, we would say that basis for the column space of A is 1, 0, -3, 2, 0, 1, 2, -3, and 1, -3, -8, and 7. Questions? So let's see. Evan asked, so would the columns from the row reduced matrix count as the standard basis? They do come from the standard basis, but they are not a basis for the column space. So yeah, the one, for example, 10000 might not even be in, is potentially not even in the column space. So the answer to your question, I think, is yes, but that's not actually helpful to you. What you want to focus on is that those pivots tell you which columns you want to look for. So let's see if we can make a connection to what these free variables are representing once again. So those free variables are telling us how we can get like non-trivial solutions. So if you took -3, the first of the, the kind of the first number in that third column, and you multiplied it by the first original column, 1 0 -3 2, and then -4. Here's the second entry in that row reduced third column, and I multiplied it by the second column in the original matrix, 0 1 2 -3. What are we going to get here? -3. Thanks, Gerline. I think the next one's also easy at -4. 1 and 6. And like Felix was saying, what we're going to get out is this vector here is the same as the original column 3. And so the entries in the in the columns without pivots basically tell you the relationships in between the columns in the original matrix, or the way it's written in the notes. Since AX equals 0 and the reduced echelon form BX equals 0 have the same solution set, and their columns have the exact same dependence relationships. And so that's what we were just showing there. Question? So Matthew asked, is this a basis for R4? And the answer is no, this is not a basis for R4. Okay, so what we've found is we found a basis for the column space of A. I know it's not a basis for R4 because there's only 3 vectors. Does that make sense, Ryan? So we got a follow-up question. So the components only matter for span. I don't understand the question. Can you ask that a different way? Okay, so in this case, all of our vectors have 4 components. And so what we're saying here, if I'm understanding your question right, what we're saying is that the column space of A is a subspace of R4. Okay. By analogy, you could go back to R2 where it's easier to draw things, and you could imagine that your column space is like a line that's living in R2. So the column space is like a line. It doesn't fill out the entire space. It just fills out a part of the space. And so the basis in the case of the line would just be any vector that's on the line. So that's by analogy. So good questions. Come on. So a note, we've already been talking about this. You've already been asking questions about this. You got to use the original pivot columns of A. So why doesn't the column space of A equal the span of B1, B2, B4? Right. If you think about the B1, B2, B4 right here, these would be like, where'd it go? Sorry, passed it. These would be like the columns B1, B2, B4 here. And you could imagine that they would always be the same spaces, right? It would always be stuff that includes the full x-axis, y-axis, and I guess that'd be z-axis in R4. And so it's like it's too simplified. So the pivot columns tell us which columns to use from A to make a basis for the column space of A. So theorem 6 says that the pivot columns of a matrix A form a basis for the column space in A. So a basis is basically the smallest spanning set possible. So you're going to remove any vectors from it, and if you remove any vectors from the basis, the set is no longer spanned. If you add any vectors to it, it becomes linearly dependent. Do you guys know the story of Goldilocks and the 3 bears? So there's a story of Goldilocks and 3 bears, and she goes into the house and she sits down with the porridge, and she sits down at the first bowl of porridge of food, and this one's too hot. And then she's like, goes to the next one. This one's too cold. And then she sits down at the little one. This one's just right. And she gets in the big bed, and this bed is too big, and this bed is too small, or, you know, is too soft. But this one was just right. So a basis is like the Goldilocks set of vectors. It's big enough to be linearly independent, but not too big to span. It's just right. Okay. So if you look at these examples that I've given here, we could say that in the first example, span R3, if we're looking for a basis for R3, that there's only two vectors there. Two vectors is not enough vectors to span all of R3. After two is not enough. Okay. If you go over to the right side, we want to span R3, and you have four vectors. I don't care what the vectors are. This is too many vectors. And so then if we look in the middle, and we could say, well, how about these three? Well, I know that I have the right number of vectors to span. Now I just got to make sure that they are linearly independent. And in this particular case, you'll notice that there's a pivot in every column. And so you can see just by inspection that these are going to be linearly independent. There's three linearly independent vectors here in R3, so they must also span R3. Therefore, they are going to be a basis. Okay. So what do we talk about today? Today we talked about the idea of linearly independent sets, okay, and bases. And we said a basis is a set that spans the space and is linearly independent. We had this crazy theorem, it had an awkward proof, but basically the point was that of all that was, if we have some extra vectors, we can just chuck them out. So if we have too many vectors, we just reorder them and chuck out all the extra ones until we have the smallest spanning set possible, and that will be our basis. Okay. Counting is not a sufficient method for finding a basis, but it is a start. And so sometimes you can just look at a set and be like, there's not enough here, so it can't span. Or maybe there's too many here, so they can't possibly be linearly independent. Okay, so sometimes that Goldilocks principle can help us figure out what's going on. So our big concept for the day and the last couple days is the concept of a basis. This is a big deal. It comes up not just in linear algebra, but in other classes. And tomorrow when we pick this up, we will use this idea of a basis to start talking about the concept of coordinates. Not just coordinates X, Y, Z that you've used in the past, but a more general idea or concept of coordinates that can apply into broader situations. So thanks everyone for a wonderful day. Thanks for hanging with me as I was dealing with more tech glitches. Have a wonderful day. Feel free to hang on the line if you have any questions. Take care, everyone.